Welcome to Lecture 23, Polar Coordinates. So, as an overview, let's compare Cartesian coordinates, which is something you're familiar with. This is just the xy plane, versus polar, which is new. In Cartesian coordinates, a point in the plane can be described by a pair xy. This is something you learned probably in middle school. And of course, x is the distance to the y-axis, y is the distance to the x-axis. Nothing new here. In polar coordinates, we describe a point in the plane by the pair r theta, where r is the distance from the point to the origin, and theta is the angle that ray makes with the positive x-axis. This is best seen with an example. So let's take a point. Now classically, up until this point, you've always called that x, and you call this y, and you say this point is x, comma y. What we're going to do now in polar coordinates is we're going to connect this point to the origin, measure the distance, and say that that's distance r. And then we're going to measure the angle that this makes with the x-axis and call that theta. And we're going to describe this point using the pair r theta. So motivation for calling this r is because you can think of this as a radius of this circle with a radius, a little r. So it's useful to, so in some cases, as we will see, polar coordinates is much more useful than Cartesian coordinates, and vice versa. It just depends on what we want to do. But it's helpful to be able to go back and forth between the two. So let's first start with polar coordinates and see how to convert polar to Cartesian. So in other words, let's do this. Polar to Cartesian. So that is given. Suppose we know the radius and the angle, we know r and theta. How do we come up with x and y? Well, that's easy. X is just r cosine theta, and y is r sine theta. So let's write that down. So given r theta, x is equal to r cosine of theta, and y is equal to r sine of theta. So that's how to go from r theta to xy. Let's go the other way around. Let's go Cartesian to polar. In other words, suppose we are given xy. So how do we get r and theta? Well, r is probably the easiest one of these. R, you can see if we know x, we know y. R is the square root of x squared plus y squared. So r is the square root of x squared plus y squared. And theta, if you think about it, theta is the inverse tangent of y over x. So theta is arctangent or inverse tangent of y over x. And let me remind you, something you've seen before, you know that there are multiple values of theta that can give you the same, multiple pairs x and y that can give you the same tangent. For example, if instead you were to pick theta plus pi, then this, which is negative x, negative y, is going to give you the same tangent as x and y. So take a little bit of care that when you're given x, y, you know right away which of the four quadrants you're in. And from that, you should be able to tell exactly which theta is correct. Okay, so I said that sometimes polar coordinate is easier, and here's an example. Let's graph the function r equals 3. So I'm going to draw the axes, xy axes, just for reference. They really don't belong there in polar coordinates, but r equals 3, so r equals 3 is just a circle of radius 3. This is a set of all points whose distance from the origin is 3. Now, how do I write this circle in Cartesian? So this is in polar. If I were to describe this circle in Cartesian coordinates, it's a lot harder. I have to say x squared plus y squared equals 9. So in this case, this is preferred. This is easier. So another example. What are the constant functions of theta? So graph the following function. Let me draw the xy coordinates just again for reference. So I am looking at, so theta equals pi over 6. So now I am looking at all points whose angle with the origin is pi over 6. So that's going to be a line of angle pi over 6. And just a technicality, it's questionable whether or not you should actually include the origin in this, because what's the angle of the origin? You could say it's that any radius would work as long as r equals 0, and there's some merit in that, but it's true. It's probably easiest to graphing this function just include the origin. Otherwise, you have a line with a hole in it. Okay, so let me see. Let me draw this thicker, and let me compare polar to Cartesian again. So in Cartesian coordinates, we draw a grid to help us visualize the coordinate system. You've done this, and you maybe not have thought about it in detail as to what this represents. But what these lines are, these lines represent constant functions. So for example, this line, so this is at y equals 1, this is y equals 2, this is y equals 3, etc. This line here is x equals 1, this is x equals 2, this is x equals 3, and so forth. So let's do the same thing. So this is x, this is y. Let's do the same thing in polar. So from what we've seen, the circle of radius 1, this is going to be r equals 1. This is the circle of radius 2, r equals 2. This is a circle of radius 3, and so forth. And then let me draw some more angles. I'm not necessarily going to label all these, but all these are supposed to all go through the origin. Well, yeah, I'll do a couple more. But hopefully you can see one of the big differences here is how do I want to draw this? Yeah, I can pick another color. So the fundamental shape in the Cartesian coordinate is we're breaking things up into squares. In polar coordinates, we're breaking things up. What's a good example? Yeah, here's one. We're breaking things up in little wedges like this, and sometimes this happens to be easier, especially if our graphs are circular shaped. As we've seen, it's easier to describe a circle in polar coordinates than a line. And just as an exercise, something to think about, I ask you to think about, well, let's actually do this here. Let's take a function. How about this one? Y equals 1. So, okay, so in polar coordinates, I've showed you how to describe okay, so we know how to describe a circle in Cartesian coordinates. This circle here is r equals 3, or it's x squared plus y squared equals 9. Let's do the opposite thing in Cartesian coordinates. Let's take this constant function and let's write this in polar coordinates. So recall that x equals r cosine of theta and y equals r sine of theta. So this constant function right here is r sine of theta equals 1. It's that function. Similarly, this constant function, I guess technically a function of y, is the set of all points satisfying r cosine of theta equals 1. So the moral of the story is, if we're working with functions that are circular, polar coordinates is often easier. If we're working with functions that have straight lines, or curves that have straight lines, Cartesian coordinates are typically easier. Okay, so let's do a more complicated example. And here I want to ask you to graph this function in polar coordinates. So this will be some curve in this plane. It might be, is it a circle? Is it an ellipse? Is it a line? It's not clear what this is. We want to find all points whose distance from the origin is 3 times the angle in radians. So to do this, we're experts at graphing things in Cartesian coordinates. So let's switch to Cartesian coordinates. That's typically a good approach. So x is r cosine of theta. So now what? Well, what we want to do is we want to eliminate r and eliminate theta. So, well, we know what r is. This is r. Let's plug that into here. That eliminates r. So r cosine theta, in other words, we are going to take that is equal to r. So this is 3 cosine of theta times cosine of theta. And this is 3 cosine squared of theta. So in other words, I'm going to write this as x over 3 equals cosine of theta. You'll see why in a moment. Let's do the same thing with y. Y is r sine of theta. Now we know what r is. R is 3 cosine theta, so this is 3 cosine of theta sine of theta. And I'm going to write this as y equals, y over 3 equals cosine of theta sine of theta. And it's not really clear what to do next. I mean, this sort of thing sometimes you have to play around with a little bit. You have to figure out what to do. One thing I'm going to do is oh, hold on, I'm missing a squared up there. Great. So let me circle both of these in blue. Okay, so what should we do? Let's start with the x one first. Let's write this as 1 plus 2 cosine of theta. Maybe not the first thing you would try, but I've done this before. I know what's coming. So let's use our double angle formula. Because what we want to do is we want to be able to solve for cosine. We want to simplify as much as possible, and typically getting rid of things like squares. So squares is going to be helpful. So let's move this down here. So this means that cosine of 2 theta is let's see. So let's do some math. I think it's 2x over 3 minus 1. Yep. So we can also use a trig identity for this one. How do I want to? Yeah, I'll do it here. So using our trig identity, we could say this is sine of 2 theta over 2. So to simplify that, we get sine of 2 theta equals 2y over 3. Should be a 3. Okay, so now I'm going to circle that, and I'm going to circle that. And, well, so we want to somehow solve for theta. This is like a lecture that we've done recently. One bad way to do that is we could take the inverse cosine of both sides and solve for theta, plug it back in, but that just makes things worse. So instead, we're going to use a trick that we've seen is put these two things together by using cosine squared plus sine squared and reducing that to 1. So said differently, so cosine squared 2 theta plus sine squared 2 theta is, well, let's write out what this is in terms of x and y, because now we have, if we do this, we have successfully eliminated theta, because this is just equal to 1. So that is 2x over 3 minus 1 squared plus 2y over 3 squared equals 1. So now we have something that looks a little more familiar. Okay, so what is this? Is this a circle? Is this an ellipse? Well, okay, so new slide. Let me copy down the last thing that we came up with. So we've determined that 2x over 3 minus 1 squared, it's supposed to be squared, plus 2y over 3 squared is 1. Okay, so how do we simplify this? Is this a circle? Is this an ellipse? Let's put in this form. So if I have x minus a squared plus y minus b squared equals r, we know what that looks like, right? That's just going to be, where do I want to draw this? I'll do it here. That's just going to be a circle centered at A, B with a radius r. So maybe that's not the best picture, but you get the idea. If it were just x squared plus y squared equals, oh, hold on, I'm going to put r squared here. Otherwise, I need to make that other one root r. So if it were x squared x squared plus y squared equals r squared, that would be centered at 0. But all this does is it shifts it a to the right and b up. Okay, so let's see if we can figure out what. Let me circle this. So let's try to put it in this form. So we'll go down here. Okay, so to do that, we need to factor out the coefficient of x and y. So I'm going to write this as 2/3 squared times, let's make sure I've done, yeah, x minus 3/2 squared. Is that correct? Let's please check. Yes, that indeed is. And then let me factor out a 2/3 again. So 2/3 squared y squared equals 1. Now we could just divide by 2/3 squared and we get that x minus 3/2 squared plus y minus 0 squared equals 3/2 squared. So this is a circle centered at, let's see, centered at 3/2 and radius, and of radius. So here a, let's do this, let's say a equals 3/2, b equals 0, and r equals 3/2. So this is a circle centered at 3/2, a radius 3/2, and yeah, that's it. And let me just say something to general. Yeah, I think that's fine. So more generally, any r equals a cosine of theta function, or r equals a sine of theta. So anytime you have an equation like this or an equation like that, that is, you can do the same steps. This is a circle, and it's shifted horizontally. How do I want to say? Let's say shifted for this one horizontally, or vertically for the other one, or vertically. With radius a over 2. Okay, here's the next example. This one looks even worse, but this is an introductory lecture, so I wouldn't be giving this to you if this were horribly ugly. And in general, it's like a Cartesian coordinates. Generally, you don't know how to graph a given equation. If I give you e to the x squared plus cosine of x or something like that, how do you graph that? Well, it's not obvious. You either plot points or you plug it into a computer. And generally, most polar functions are going to be the same thing. It's not obvious how to do it. Obviously, you don't have as much experience as you do with Cartesian. So the ones you're going to get are going to be ones that are fairly straightforward. Okay, so let me remind you, we're trying to turn this, so to graph this, we would like to turn it into Cartesian coordinates because we know how to graph those. So remember that x equals r cosine theta and y equals r sine theta. Let's make that more of a sine. And now, do you see any r cosines and r sines in here? Well, if you take this and you multiply it over to the left-hand side, you get an r cosine and you get an r sine, and we can get rid of those and turn them into x's and y's. So in other words, let's write this as r times 2 cosine of theta minus sine theta equals 4. So I'm going to write this as 2r cosine of theta minus r sine theta equals 4. Notice this is equal to x. This is equal to y. So this thing simplifies right away to 2x minus y equals 4. And since I went through the public school education system, I cannot graph this unless I put it in y equals mx plus b form. So that's y equals 2x minus 4. We know what that looks like. That's a line whose slope is positive 2 and whose y-intercept is 4. So hopefully you can see how to generalize this. If you want to, you can work backwards. Suppose you start with y equals mx plus b. We can do these steps in reverse. How do I want to? Yeah, so I guess to do this we could let's be careful here. Mx minus y equals negative b. All right, and then I'm not organizing this very well. So I'm just checking to make sure. Yeah, so then let's back up a little bit. I can write this as m r cosine of theta minus r sine of theta equals negative b. And let's finish down here. Now you can factor out the r, and you can get that r equals negative b over m cosine of theta minus sine of theta. Hey, look what I've done. I've just derived the equation for a line y equals mx plus b and polar coordinates. Not something you would have guessed, right? Okay, here's a fun topic. We're just going to scratch the surface of this. If you take multivariable calculus or vector calculus, that's, I think, math 20, or now it's 2060. You'll see more. It's about area and integration in polar coordinates. So let's start with what we know in Cartesian coordinates. Let's suppose we have a function. This is f of x. So y equals f of x, and we want to compute the area between a and b, area under the curve. So this is so we're saying compute the area under the curve between the constant function x equals a and the constant function x equals b. And you know how this works. What happens is you break this thing up into small pieces, and it ends up being a bunch of Riemann sums, and you take the limit. So I will refer you to the book for a proof. Okay, well, I'm getting ahead of myself. Okay, so let's write that down. So the area is, I can write that a little better. The area is from x equals a to x equals b of f of x dx. And remember, the reason why it's f of x times dx is you can think of this as the base has width dx. So the area of each box is dx, that's the base, and then the height is f of x. So how do I want to say that? Let me do this. Call this the height equals f of x. Okay, so let's do a similar thing in polar coordinates. Let's suppose we have a function. R equals f of theta. And we could, of course, have a function theta equals g of r. Just like how we have y could be a function of x, or x could be a function of y. Or a curve might not be a function at all, but I think r equals f of theta is a little bit easier to think about. So at each angle, we have to specify how far we are from the origin. So we have something like this. And let's compute the area between the constant function. Let's say this is theta equals alpha. And let's say this is the constant function theta equals beta. So how do we compute the area? Well, what we're going to do is, I'm not going to prove this, but I'll give you the picture proof, and I'll refer to you to the book for details. But really, once you get the picture, that's the gold standard. That's really all you need, especially for this class. Okay, so we want to break this up into infinitesimal pieces, sort of like Riemann sums. However, our infinitesimal pieces are going to look like this. So we're not actually going to have Riemann sums of boxes. What we're going to have is we're going to have Riemann sums of triangles. Something like that. And we add up the area of the triangles. So, informally, the area, well, let me go up here and say the area is the limit as delta x goes to 0 of the sum of boxes. Really informal, because I don't want to overburden you with notation. You've seen this before. So down here, the area is the limit of, let me just say the base of the triangles go to 0 of the sum of triangles. So think of this as Riemann sums of triangles. So what is the area of a triangle? Let's see. So how do I want to organize this? So I'm going to pull out a triangle here. So let's do this. Okay, so this line has height. What's the height of this line? The height of this is equal to f of theta, right? Now, what's the base of this triangle? I'm going to say d theta, right? That's not quite right. D theta is the angle. I guess if I wanted to be correct, I should say delta theta. And then in the limit, that becomes d theta. But I'm fine with just working with calling this dx and calling that, yeah, so I said dx, technically it should be delta x, but this stuff is below us, and then we take the limit. Okay, so I'm going to say that the base of this is dx, and I'm going to say that the angle of this is, so let's say that the angle is d theta. So what's this length? Well, let me draw a picture on the side. Now, what if how do I want to do this? What if I have a circle of radius r of, oh, no, let me call it lowercase r. What if I have a circle of radius r and I have a little angle, this is angle theta, then this arc length is just r times theta. Let's see why. Notice if theta is 2 pi, then r times theta is just 2 pi r, the circumference. So if theta is any proportion of 2 pi, then the arc length is that particular proportion of the circumference. So in other words, this base is r, the radius, times d theta. And the height is f of theta, which is just r. Remember, r equals f of theta. Okay, so to summarize, again, I'm trying to figure out how to best organize this. Okay, let's do that. So area is the integral from theta, I'll put area here, theta equals alpha to theta equals beta of base times height, which is, oh, there's one little tiny detail I forgot. We have a triangle here, right? So the area of the triangle is 1/2 base times height. So let me just say that first. The area of the triangle equals 1/2 base times height, which is 1/2 r squared d theta. So our area formula is 1/2 r squared d theta. And that, I think that's a really cool result. Or especially how that matches the picture so well, and how you can just do the same thing we did with the Riemann sums, but you do it for Riemann triangles. And if you like that, then you should take Math 206 or 2060 vector calculus next semester. Let's do an example of what we just learned with area. So here's a problem. Find the area of the region that lies inside the circle r equals 3 sine theta, and outside the cardioid, or that's derived from heart-shaped. It's either Latin or Greek, I'm not sure which. I'm not even sure I pronounced it correctly, but I'm not going to say it again. So the heart-shaped region, r equals 1 plus sine theta. So first of all, it should not be clear what this thing is. And I encourage you to plug it into a graphing calculator to see what you get. But let's try to reason through what it should look like roughly. Okay, so we saw in example 3 that this is in fact a circle of radius 3/2 and centered at 3/2. So it's going to look something like that, and this is 3/2, and this here is 3. We know that. And let's try to figure out what this thing looks like. So this is the set of all points where the radius is 1 plus sine theta. Okay, so what's the largest this thing can be is 2, right? Sine theta, the largest that ever is 1. And sine theta is equal to 1 when theta is 90 degrees. So in other words, when theta is pi over 2, or on this ray, then r equals 2. So let's try that. Equals pi over 2. So theta equals pi over 2, r equals 1 plus sine of pi over 2 equals 2. So if theta equals pi over 2, we are up. So we're right here. Okay, what about theta equals 0? R equals 1 plus sine 0. That's equal to 1. Okay, so on the x-axis, theta equals 0. So this here is 3/2, so I need to go a little bit less than 3/2. So that's going to be 2. This is going to be, that's going to be 1. Where do I want to, I'll do that there. That's going to be 1. This of course here is 3/2. Maybe in that case I shouldn't have drawn 1 there. Maybe I should draw 1 there. Similarly, for theta equals pi, r is also going to be 1 plus 0 equals 1. So this thing is going to intersect, I meant to do that in red, that point. Okay, so what about theta equals 3 pi over 2? At 3 pi over 2, sine is equal to -1. So now r equals 1 plus -1, which is 0. So along this axis, r is actually 0. It's right there. And if you think about, as r changes as r goes from pi to 2 pi in this region, sine, S-I-N, sine of theta is always negative in this region. So 1 plus something negative is going to be something less than 1. So if this is the circle, radius 1, our carotid, I guess I said I wouldn't say it again, but I forgot. This region is going to be inside of this circle, so it's going to be smaller, and in fact it's going to connect, look something like that, something like that. It's got to connect these 3 points, and it's got to sit inside of the circle of radius 1, because r is going to be 1 plus something less or something negative. And so this is going to connect up like that, and this is going to connect up like that. So I said you should graph it, but actually, even though this was not obvious what this was, we plotted a few points and we reasoned through it. So now let's go back and re-examine this problem. Find the area of the region that lies inside the circle and outside of the heart-shaped region. So that is be this piece right here. Find that. So that is going to be, so let's set up the integral. So the area is 1/2 theta equals, oh, I don't know. So I'm going to leave this blank for now. R squared d theta. So first of all, let's fill in these blanks. That point of intersection, that is the line. So what line is that? That is, what's that angle? And let me ask the same thing about this line. This line is theta equals something, and this line is, well, I've run out of room. Theta equals, no, how do we find that? Okay, so I'm just thinking about organization. Let's do it up here. Points of intersection. So how do we find these? Well, let's set the two curves equal to each other. R is 3 sine theta. When is that equal to 1 plus sine theta? So 3 sine theta equals 1 plus sine theta. So let's see, we can subtract theta, or we can subtract sine of theta, and we get sine of theta equals 1/2. I skipped an algebra step, but I'm sure you can handle that. So so that's saying sine of theta. Sine of theta equals 1/2. Let's draw the unit circle. That of course happens. That's where the y-axis and the unit circle is equal to, or the y-coordinate is equal to 1/2. That happens at theta equals pi over 6 and 5 pi over 6. So this is pi over 6, and this guy is 5 pi over 6. So let's write that down here. So we are integrating pi over 6 to 5 pi over 6, 1/2 r squared d theta. What is, let's see, so what's r squared? Actually, well, let's see. So let me ask you this question from calculus. If I said compute the area between f of x and g of x from a to b, if I said compute that area, so what you want to do is you want to compute just this area. You can think of that as the blue area minus this red area. So in other words, in this case, area is the a to b f of x dx minus a to b g of x dx, or we can write this in a single integral as f of x minus g of x dx. So similarly here, we want to compute this entire area under the blue curve minus the area under the red curve. So let's, we want to subtract this off. So maybe I want to write this as, so we want to take this entire blue area and subtract off the red area. So I'm going to write this as 1/2 pi over 6, 5 pi over 6. This first curve, this circle, that is equal to this. So r squared is 3 sine of theta squared. And then the lower curve, this guy, that's r equals 1 plus sine theta. So minus 1 plus sine theta squared d theta. Now I'm running out of room, so let me separate that. Okay, so this is 1/2 pi over 6 to 5 pi over 6 of 9 sine squared of theta minus 1 minus 2 sine theta plus, no, I'm sorry, not plus, minus sine squared theta d theta. Okay, I hope I can fit this in here. So, so for the next couple integrals, I'm just going to leave out the pi over 6 and 5 pi over 6, and I'll put that back in later. So this is, how do I want to simplify this? Let's see. You know what I think I'm going to do? 5 pi over 6 is not the friendliest of angles, because I'm going to have a root 3 over 2. So it should be clear that this area is just twice of this area, right? Just by symmetry. So let's integrate from pi over 6 to pi over 2. It's a much nicer angle. And then just double it. Okay, so this is twice times 1/2 times pi over 6. That should be pi over, let's make that a little better. It's hard to write these things smaller. Pi over 6 on the bottom and pi over 2 on top. Now what do we have here? We have 8 sine squared theta. We have minus 1. We have minus 2 sine theta d theta. Right? Now, we know how to simplify 8 sine theta. Typically, that's easier to do the double angle formulas. I'm going to save my space and recall up here that that's 1 minus cosine of 2 theta over 2. Okay, so let's simplify this, and again, I hope I have room. I think I can squeeze this in here. So we are integrating from pi over 6 pi over 2 so that's going to be 8 times 1/2 minus 1, that is going to be a 3. That's going to so how many cosines do we have? We have 8 times negative 1/2, so that's minus 4 cosine of 2 theta. And we still have minus 2 sine of theta left. Okay, good. I think we can squeeze it in here. So we know how to integrate these things. This is really easy. So integral of this is 3 theta minus 2 sine of 2 theta plus 2 cosine of theta. Let's integrate this from pi over 6 to pi over 2. And what do we get? Let's see. Hope I can squeeze this in here. So let's plug in pi over 2 first. So the first term is going to be 3 pi over 2. Okay. Now, 2 sine of 2 pi, or 2 theta. So twice the angle, that's 2 sine of pi. Sine of pi is 0. So that's minus 0. And then the last one is 2 cosine of pi over 2. Cosine of pi over 2 is 0. So that's going to be plus 0. Okay. Now let's subtract what we get when we plug in pi over 6. So that should be equals. So subtract, we plug in pi over 6. 3 times pi over 6 is pi over 2. Okay, next one. Let's plug in pi over 6 into here. Negative 2 times sine of twice pi over 6. Sine of, okay, so that's sine of pi over 3. That's 1/2. So minus 2 times 1/2. That's minus 1. And now this last term, 2 cosine of pi over 6. Cosine of pi over 6 is 1/2. We've seen that. That's over here, just the x-coordinate. So that's going to be plus 2 times 1/2, which is plus 1. That works out nicely. The 1 and minus 1 cancel, and our final answer is plain and simple, pi. Okay, so the last topic, I want to mention something briefly that occurs in polar coordinates that does not, this is a little anomaly, that does not happen in Cartesian coordinates. So in Cartesian coordinates, every single point is represented by a unique x and a unique y. And that's almost true in polar coordinates, but the one problem point is the origin. This is represented by, if r equals 0, well, r has to be 0, but then theta can be anything, any angle. So because of this technicality, there's a slight discrepancy in points of intersection of two curves. So there's two types, and I'll go over these. So a point of intersection of two polar curves, f of theta, g of theta, is just any point that's on the graph of both curves. Now, a point of intersection is, moreover, a point of collision if this happens for the same value of theta. So you can think of polar curves as being parameterized. You can think of theta as being time if you want. So our bug is starting at time 0 and going up to 2 pi and walking along this curve. Let's do an example to illustrate this. Let's take the curves that we did from the previous slide. So let's say that r equals, what was the first one? 3 sine of theta. So at theta equals, let's see, so theta, let's say it starts at 0. At theta equals 0, we are right here. And then as theta increases, we go up like this and over, and we arrive back at the origin. So this is theta equals 0. We arrive back at the origin at theta equals pi. I should say that we really should end at pi. I mean, it's not wrong to go up to 2 pi, but we're not going to get any extra points. If pi is like between pi and 2 pi, there's no solutions, because that would force this side to be negative, and there r cannot be negative. So it's like saying, Cartesian coordinates, if we say like x squared equals 5 or negative 5, we don't actually get any extra points. Or no, that's not a great example. What's a better example? Something like square root of x. We can put in negative, the graph of that. The domain is from 0 up to infinity. We don't get anything extra by allowing points in here. We don't get any more points on this curve by allowing negative inputs, because we just don't get any outputs for that. Okay, so it really should restrict the domain from 0 to pi. For the next curve, this was r equals 1 plus sine of theta. Here, at theta equals 0, along the x-axis, we are starting here. So this is the point, remember, where theta equals 0. And in this case, now when we increase, we go up to here. Then we go back down to here, and then we have this little heart-shaped. So this point, maybe I should have drawn this bigger. Oh well. This point of intersection happens at theta equals, no, not equals. I'm not even going to try to guess what R is. Oh, actually, yeah, we know what. Yeah, so theta equals, and we have a formula for it. So theta equals pi over 6. This point of intersection happens when theta equals 5 pi over 6. So both of these are points of collision. So just because these points are on both graphs, they are by definition points of intersections. But they are also points of collisions because they happen for the same value of theta. So let's see, what is that value of theta? So what is sine of pi over 6? So sine of pi over 6 is 1/2. So this r, so r equals 3 sine of pi over 6, which is 3 times 1/2. So that's 3/2. Oh, of course it's 3/2, because, well, not of course. But yeah, actually it's not quite clear that it should be, but it's just a little geometry exercise to take the center of the circle to see that you should get an equilateral triangle, I would assume. Okay, so the points of collision, I digress, are r theta equals 3/2 and pi over 6. There's one of them. Another one is 3/2 and 5 pi over 6. So here our blue ant and our red ant, why am I thinking about Tron in this example, collide right here, and then they collide here. Now there's one more point of intersection of these two graphs, and it's the origin. However, our blue ant is at the origin at theta, or time, equals 0, and t equals 0, and t equals pi. Whereas our red ant is at the origin at theta equals 3 pi over 2. So there's a point of intersection that's not a collision. It's not a collision point, and this happens at r equals 0. And it's enough to not even specify the angle because, well, the angles are different, but when I say r equals 0, you know that's going to be at the origin. So how do I want to say this? How about, so the first curve, so r theta equals 0, 0, and compare that to, that's at the origin, and the other curve passes through at, so r theta equals radius is 0, but now theta is 3 pi over 2. So though both the red ant and the blue ant visit this point, they do so at different times. You convince yourself that this origin, this is really the only issue, the only time that one of these points of collision is ever going to happen without, or sorry, a point of intersection is going to happen without a point of collision.